This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Welcome. Ever wondered why there are only 5 Platonic solids? These mesmerizing 3D shapes, with their perfect symmetry, have captivated thinkers for centuries. Join us as we unlock their secrets, using clear and simple explanations. We'll explore their unique properties, uncover the mathematical reasons behind their limited number, and discover how these ancient forms appear in nature, from crystals to viruses. Get ready for a fascinating journey into the world of geometry and its hidden connections to the universe around us. Chapter 1. The Whispers of Ancient Greece. Imagine holding a perfect crystal in your hand, its facets gleaming with an otherworldly symmetry. Its form is so precise, so balanced, that it seems to hum with an inner harmony. This is the allure of the Platonic solids, 5 unique three-dimensional shapes that have echoed through the corridors of time, whispering secrets of the universe to those who listen closely. For millennia, these enigmatic forms have captivated mathematicians, philosophers, and mystics alike, their perfect symmetry hinting at a deeper order underlying the apparent chaos of the world. Named for the ancient Greek philosopher Plato, who explored their significance in his dialogues, the Platonic solids are distinguished by their remarkable regularity. Each face of a Platonic solid is an identical, regular polygon. Not just any polygon, but one where every side is the same length and every angle is equal. Furthermore, at each corner, or vertex, of a Platonic solid, the same number of these identical polygons meet. It's as if a divine hand meticulously crafted these shapes, ensuring absolute balance and harmony in every detail. Let's acquaint ourselves with these 5 celestial forms. The simplest, the tetrahedron, rises from a base of 3 equilateral triangles, culminating in a 4th, forming a perfect triangular pyramid. Picture the strength and stability of a pyramid, distilled into its purest geometric form. Next, the familiar cube, or hexahedron, stands as a testament to order and structure, its 6 square faces meeting at perfect right angles. Then, the octahedron, a delicate dance of 8 equilateral triangles, resembles 2 square pyramids joined at their bases, its form suggesting lightness and airiness. The dodecahedron, with its 12 pentagonal faces, presents a more complex and intriguing structure, its intricate form whispering of hidden knowledge. Finally, the icosahedron, a mesmerizing tapestry of 20 equilateral triangles, shimmers with a near-spherical grace, its numerous faces hinting at the fluidity and complexity of the universe itself. The ancient Greeks, with their keen eye for beauty and their relentless pursuit of knowledge, were deeply fascinated by these shapes. They saw in their perfect symmetry a reflection of the divine order they believed permeated the cosmos. Plato, in his dialogue Timaeus, associated 4 of the solids with the classical elements. The tetrahedron with fire, its sharp points evoking the element's flickering flames. The cube with earth, its sturdy structure mirroring the earth's solidity. The octahedron with air, its lightness and delicate balance reflecting the ethereal nature of air. And the icosahedron with water, its numerous faces and near-spherical form suggesting fluidity and change. The remaining solid, the dodecahedron, was reserved for the universe itself, or the ether, a 5th element believed to fill the heavens. This association with the fundamental elements elevated the Platonic solids from mere geometric curiosities to symbols of the very fabric of reality. Evidence of this ancient fascination stretches back further than Plato's writings. In Scotland, archaeologists have unearthed carved stone balls dating back to the late Neolithic period, some bearing markings reminiscent of the Platonic solids. While their exact purpose remains shrouded in mystery, these artifacts suggest that an awareness of these special shapes predates even the ancient Greeks, hinting at a deeper, perhaps intuitive, understanding of their significance. Centuries after Plato, the German astronomer Johannes Kepler, in his quest to understand the structure of the solar system, attempted to link the Platonic solids to the orbits of the then-known planets. In his book Mysterium Cosmographicum, he proposed a model in which the 5 solids were nested within one another, separated by spheres representing the planetary orbits. While ultimately incorrect, Kepler's model demonstrates the enduring power of these shapes to inspire and guide scientific inquiry. Even Euclid, the father of geometry, dedicated the final book of his monumental work, The Elements, to the construction and properties of the Platonic solids, further solidifying their place at the heart of classical geometry. Some even whispered that the construction of these 5 solids was the ultimate goal of Euclid's entire deductive system, the culmination of his geometrical explorations. It was as though these shapes, so simple yet so profound, held the key to unlocking the secrets of space itself. But the most intriguing question surrounding the Platonic solids remains: why only 5? In the two-dimensional world, we can construct an infinite number of regular polygons, triangles, squares, pentagons, hexagons, and so on, each with equal sides and angles. Yet, when we venture into the third dimension, this boundless possibility collapses into a finite set of 5. Why this sudden restriction? Why does nature, so often extravagant in its creations, suddenly exercise such restraint? The answer, as we shall discover in the chapters that follow, lies hidden within the very geometry and topology of these shapes. The way their faces meet at vertices, the relationship between their vertices, edges, and faces, these properties, so carefully defined, impose strict limitations on the possible forms that can exist. Even the Schläfli symbol, a concise notation used to describe polyhedra, hints at this underlying order, each Platonic solid possessing a unique symbol that reflects its specific structure. Our journey has just begun. We stand at the threshold of an ancient mystery, ready to delve into the mathematical depths and uncover the reasons behind this remarkable limitation. Join us as we explore the whispers of ancient Greece and unravel the secrets of the 5 Platonic solids. Chapter 2. The Dance of Angles. But the whispers turn to a resounding question: why only 5? Why, in the boundless expanse of three-dimensional space, are we limited to this quintet of perfect forms? The answer lies in the delicate dance of angles at the vertices of these solids, a geometric ballet with very specific rules. Imagine a vertex, a corner point of a three-dimensional shape. It's where the edges of the shape meet, the point of convergence for its faces. Think of the corner of a cube, where 3 squares come together. This meeting point, this vertex, is the key to understanding the limitations of the Platonic solids. For a solid to exist, a vertex must be formed by the meeting of at least 3 faces. 2 faces meeting would simply create a fold, a 2-dimensional bend, not a 3-dimensional corner. So, 3 is our minimum. But there's another, more subtle constraint. The sum of the interior angles of the faces meeting at a vertex must be less than 360 degrees. Visualize this. If the angles add up to exactly 360 degrees, the faces would lie flat, creating a tiling pattern on a plane, not a solid angle. Imagine 6 equilateral triangles meeting at a point. Each triangle's interior angle is 60 degrees, so 6 of them add up to 360 degrees. They tessellate perfectly, creating a beautiful hexagonal tiling, like a honeycomb, but not a solid vertex. If the angles sum to more than 360 degrees, the faces simply wouldn't fit together in 3-dimensional space. They'd overlap, creating a concave, inward-pointing corner, violating the convexity requirement of Platonic solids. Let's start our exploration with the simplest regular polygon, the equilateral triangle, each angle a crisp 60 degrees. 3 triangles meeting at a vertex sum to 180 degrees, well below our 360-degree limit. Fold them together, and you create the sharp peak of a tetrahedron, our first Platonic solid. 4 triangles at a vertex total 240 degrees, still within bounds. This arrangement gives us the octahedron, its vertex less pointed than the tetrahedrons. 5 triangles sum to 300 degrees, forming the nearly spherical vertices of the icosahedron. But 6 triangles, as we saw earlier, bring us to 360 degrees, the flat hexagonal tiling. Trying to force more triangles around a vertex would be like trying to fold a piece of paper more times than physically possible at a single point. The paper resists, the angles fight back, and the flat plane stubbornly refuses to become a solid corner. Now, consider the square, a sturdy 90 degrees at each angle. 3 squares meeting at a vertex total 270 degrees, forming the familiar corner of a cube. But 4 squares bring us to 360 degrees, a flat square tiling, like a checkerboard stretching infinitely in all directions. Again, we reach a limit. The paper, cut into squares, can be folded to create 3 sides of a cube, but that 4th square stubbornly refuses to bend into the 3rd dimension. Finally, the regular pentagon, its angles a more complex 108 degrees. 3 pentagons at a vertex sum to 324 degrees, forming the vertex of the dodecahedron, a shape that feels almost too complex to be real. But 4 pentagons would total 432 degrees, exceeding our limit. Try to construct this with paper pentagons, and you'll find they won't even lie flat. The angles force the pentagons to buckle and overlap, defying the rules of our geometric dance. What happens when we move beyond the pentagon? The regular hexagon, with its 120-degree angles, offers a clue. 3 hexagons at a vertex already totaled 360 degrees, a flat hexagonal tiling, like the cells of a honeycomb. No solid vertex can be formed. As we progress to heptagons, 128.57 degrees, octagons, 135 degrees, and beyond, the interior angles continue to increase. Even 3 of these polygons meeting at a vertex would exceed 360 degrees, making them unsuitable for constructing Platonic solids. They too, like the hexagons, create their own unique tiling patterns, endlessly repeating across the plane. This dance of angles reveals a profound truth about the Platonic solids. It's not simply that there happen to be 5, it's that the very nature of angles and polygons, the fundamental building blocks of 3-dimensional geometry, allows for no more. The limitations are not arbitrary, they are woven into the fabric of space itself. And as we explore further, we'll discover even deeper connections between these 5 solids and the mathematical structures that govern our world. Chapter 3. Euler's Jewel. We've seen how the dance of angles elegantly explains why only 5 Platonic solids can exist. But there's another, even more profound way to understand this limitation, a path that leads us through the fascinating realm of topology. This path is illuminated by a remarkable formula, a true jewel of mathematics, discovered by the Swiss polymath Leonhard Euler. Euler's formula, a cornerstone of topology, connects the number of vertices, v, edges, e, and faces, f, of any convex polyhedron in a surprisingly simple way. V, E plus F equals 2. It's a formula that seems almost too good to be true. How can such a simple relationship hold for such a diverse array of shapes? Let's test it out. We've already looked at the cube. It has 8 vertices, 12 edges, and 6 faces. Plugging these values into Euler's formula, 8 minus 12 plus 6 equals 2. It works. The tetrahedron, with its 4 vertices, 6 edges, and 4 faces, also fits the bill. 4 to 6 plus 4 equals 2. But Euler's formula isn't just a descriptive tool. It's a powerful constraint on the very existence of certain shapes. It arises from the fundamental topology of these solids, their sphere-like nature. Imagine taking any convex polyhedron and inflating it like a balloon. The resulting shape, regardless of the original polyhedron's specific form, would be a sphere. This transformation preserves a fundamental topological property, the relationship between vertices, edges, and faces, captured by Euler's formula. This relationship is a topological invariant, a property that remains unchanged under continuous deformations, like stretching or bending. Think of a donut and a coffee cup. A coffee cup has a handle, and a donut has a hole. Topologically, they are equivalent. You can imagine deforming a clay coffee cup into a donut shape without cutting or gluing. Euler's formula, applied to such shapes, would yield a different invariant, reflecting their donut-like topology. Now, let's see how Euler's formula restricts the possibilities for Platonic solids. Recall that a Platonic solid is constructed from identical regular polygons, with the same number of polygons meeting at each vertex. Let n be the number of sides of each polygon, the face, and m be the number of faces meeting at each vertex. For example, for a cube, n equals 4 squares, and m equals 3 squares meet at each vertex. We can express the total number of edges, e, in 2 ways. First, since each face has n edges and there are f faces, we have NF edges. But each edge is shared by 2 faces, so we've counted each edge twice. Therefore, E equals NF 2. Second, since M faces meet at each vertex, and each face has in edges, there are MV edges emanating from all vertices. Again, each edge connects 2 vertices, so we have E equals MV 2. Substituting these 2 expressions for E into Euler's formula, V, E plus F equals 2, we get V, NF, 2 plus F equals 2. We also know that V equals 2E per meter, so substituting this expression for V into our modified Euler's formula, we get 2E per meter, NF, 2 plus F equals 2. Now, we have a single equation with E, F, N, and M. Let's divide the entire equation by 2E to simplify. 1 per meter, N, 2, F, E, plus F, E, 1/2, equals 1. E we know that F, E equals 2, N from E equals NF, 2. Substituting F, E equals 2, N in the previous equation, we get 1 per meter, N, 2 asterisk, 2, N, plus 2, N, 1/2, equals 1, E, which simplifies to 1 per meter 1 plus 1, N equals 1, E. Rearranging this, we arrive at the crucial inequality. 1, N plus 1 per meter greater than 1/2. Remember, N and M must be integers greater than or equal to 3, representing the number of sides per face and the number of faces meeting at a vertex, respectively. This inequality is the gatekeeper, allowing only a select few combinations of N and M to pass through. Let's enumerate the possibilities. If N equals 3 triangles, M can be 3, 4, or 5, giving us the tetrahedron, N equals 3, M equals 3, octahedron, N equals 3, M equals 4, and icosahedron, N equals 3, M equals 5. If N equals 4 squares, M can only be 3, yielding the cube. If N equals 5 pentagons, M can only be 3, giving us the dodecahedron. If N equals 6 hexagons, or greater, no integer value of M satisfies the inequality. There they are, the 5 solutions, each corresponding precisely to one of the 5 known Platonic solids. It's a moment of pure mathematical magic. A seemingly simple formula, relating vertices, edges, and faces, reveals a profound truth about the universe of shapes, a limitation so unexpected, so elegant, that it takes one's breath away. This unexpected finiteness, derived from a simple formula about vertices, edges, and faces, is a testament to the power of topology. It underscores the profound connection between seemingly disparate mathematical concepts, revealing a hidden order in the world of shapes that might otherwise remain unseen. The 5 Platonic solids, once mere geometric curiosities, now stand as tangible expressions of this underlying mathematical harmony, their perfect symmetry echoing the elegance of Euler's jewel. Chapter 4. Beyond the 5. We've explored the perfect symmetry of the Platonic solids, those 5 exquisite forms that seem to embody cosmic harmony. But what lies beyond these paragons of geometric perfection? What happens when we relax the strict rules that define them, allowing for a little less perfection, a touch of asymmetry? A whole universe of fascinating polyhedra awaits, each with its own unique story to tell. Let's begin with the Archimedean solids, a family of polyhedra that share some, but not all, of the Platonic solids' characteristics. Like their more famous cousins, Archimedean solids are convex, their faces meeting only at their edges. However, they differ in one crucial respect. They can have more than one type of regular polygon as faces. It's as if they represent a more democratic society of shapes, where different polygons can coexist in harmony. Imagine taking an icosahedron, that shimmering jewel of 20 equilateral triangles. Now, imagine slicing off each of its 12 vertices, just enough to create a new face where each vertex once resided. These new faces are regular pentagons, and the original triangular faces, now truncated, become hexagons. The result is the truncated icosahedron, a shape familiar to anyone who's ever held a soccer ball. This fascinating polyhedron boasts 60 vertices, where 2 hexagons and 1 pentagon meet at each corner. It's a beautiful example of how a simple modification can lead to a new, complex, and even practical shape. The truncated icosahedron is just one member of the Archimedean family. Consider the truncated cube. Starting with the familiar cube, we slice off each of its 8 vertices, creating 8 new triangular faces. The original square faces, now truncated, become regular octagons. The resulting truncated cube has 24 vertices, each formed by the meeting of 2 octagons and 1 triangle. It's a fascinating blend of squares and triangles, transformed into octagons and triangles by the simple act of truncation. Another intriguing Archimedean solid is the truncated octahedron. This time, we begin with the octahedron, that delicate dance of 8 triangles. Slicing off each of its 6 vertices, we create 6 new square faces. The original triangular faces, truncated, become hexagons. The truncated octahedron has 24 vertices, each formed by the meeting of 2 hexagons and 1 square. It's an elegant example of semi-regularity, a property shared by all Archimedean solids. Semi-regularity refers to the combination of regularity and variety in these shapes. While they use more than one type of regular polygon, the arrangement of these polygons around each vertex is identical. This consistent vertex configuration is what distinguishes Archimedean solids from other polyhedra with mixed faces. It's a subtle but crucial distinction, a balance between order and diversity. Now, let's venture even further beyond the familiar, into the realm of Kepler-Poinsot polyhedra. These intriguing shapes break another rule of the Platonic solids, using star polygons as faces. Star polygons are not your typical polygons. They are formed by extending the sides of a regular polygon until they intersect, creating a star-like pattern. It's as if the polygons have reached out and grasped each other, creating a new, more complex form. The small stellated dodecahedron is a striking example of this. It's constructed from 12 pentagrams, 5 pointed stars formed by extending the sides of regular pentagons. These pentagrams intersect and intertwine, creating a mesmerizing, almost otherworldly shape. It's a form that challenges our conventional notions of what a polyhedron can be. Another Kepler-Poinsot polyhedron is the great icosahedron. This intricate shape is formed from 20 intersecting equilateral triangles, arranged in a star-like pattern. The triangles intersect in such a way that the resulting solid is non-convex, with inward-pointing vertices. It's a complex and beautiful form, a testament to the surprising diversity that arises when we allow for self-intersecting faces. So far, we've explored polyhedra with regular polygon faces and identical vertex configurations. But what happens when we relax the rule about the same number of faces meeting at each vertex? Can we still create interesting shapes with regular polygon faces? Consider a solid constructed entirely from equilateral triangles. Some vertices have 5 triangles meeting, while others have 6. This variation in vertex configuration immediately disqualifies it from Platonic status. However, it still results in a fascinating polyhedron, a testament to the flexibility of triangles as building blocks. You can visualize this shape by imagining a partially flattened icosahedron, where some vertices are pushed inward, creating 6 triangle meetings, while others remain in their original positions, retaining their 5 triangle meetings. It's a shape that straddles the boundary between regularity and irregularity. Finally, let's delve into the world of non-convex polyhedra. Concavity, the presence of indentations or cavities, is another violation of the Platonic solid definition. Imagine taking an icosahedron and denting one of its faces inward. The resulting shape is no longer convex, as the dented face creates a cavity. Alternatively, picture a cube with a smaller cube removed from its center. This hollowed-out cube is also non-convex, its internal cavity creating an inward-pointing surface. These non-convex polyhedra, while lacking the perfect symmetry of the Platonic solids, offer a glimpse into an even wider world of shapes, where concavity and irregularity create their own unique forms of beauty. Our exploration beyond the 5 Platonic solids has revealed a rich and varied landscape of polyhedra. From the semi-regularity of Archimedean solids to the star-studded Kepler-Poinsot polyhedra, and from the varied vertex configurations of triangle-faced solids to the intriguing concavity of non-convex forms, we've encountered a diverse array of shapes, each with its own unique characteristics. While none possess the complete symmetry and regularity of the Platonic solids, their existence reminds us that beauty and fascination can be found even in imperfection. They are a testament to the boundless creativity of geometry, a reminder that even within the constraints of mathematical rules, there's always room for surprise and wonder. Chapter 5. Nature's Blueprint. Let's begin our exploration with crystals, those natural wonders that embody order and symmetry. Crystals aren't simply beautiful, their structure reflects the precise arrangement of atoms within a microscopic architecture governed by the laws of geometry. Take the common salt crystal, for example. Its cubic form isn't merely a coincidence, it's a direct consequence of the underlying atomic lattice. Sodium and chloride ions, the building blocks of salt, arrange themselves in a repeating three-dimensional grid, a cubic lattice where each sodium ion is surrounded by 6 chloride ions, and vice versa. This arrangement maximizes stability and minimizes energy, a testament to the efficiency of the cubic structure. But the cubic lattice isn't the only game in town. Diamonds, those symbols of enduring strength and brilliance, boast an octahedral structure. Here, carbon atoms bond together in a tetrahedral arrangement, forming a lattice that repeats in 3 dimensions to create the octahedral form. This tightly packed structure is responsible for the diamond's exceptional hardness and its ability to refract light, creating its characteristic sparkle. Different crystal systems, each with its own unique arrangement of atoms, can give rise to a variety of Platonic solid forms, showcasing the versatility of these geometric blueprints. Now, journey with us to the microscopic realm of viruses, those tiny packets of genetic material that can wreak havoc on living organisms. Many viruses, including the adenovirus and the herpes simplex virus, enclose their genetic payload within a protein shell called a capsid. And what shape do these capsids often adopt? The icosahedron. This remarkable shape, with its 20 triangular faces, provides an ingenious solution to a viral conundrum: how to maximize internal volume for storing genetic material while minimizing the number of protein components needed to build the shell. The icosahedron's high volume to surface area ratio makes it the ideal container, a natural choice for viruses seeking to optimize their structure for efficient replication. From the microscopic to the almost microscopic, we encounter radiolarians, single-celled marine organisms with intricate silica skeletons. These skeletons, often breathtaking in their complexity and beauty, frequently exhibit Platonic solid forms. The Circagonia icosahedra, as its name suggests, boasts a skeleton resembling an icosahedron, its delicate structure providing support and protection in the marine environment. Other radiolarian species showcase tetrahedral, octahedral, and even dodecahedral forms, demonstrating nature's creative use of these geometric blueprints in the microscopic world. These geometric forms not only provide structural integrity but also influence the radiolarian's interaction with their environment, affecting their buoyancy and movement through the water. Next, let's explore a more recent discovery: fullerenes, those fascinating carbon molecules that have revolutionized materials science and nanotechnology. The most famous fullerene, C60, also known as a buckyball, resembles a truncated icosahedron, the very same shape as a soccer ball. Its 60 carbon atoms are arranged in a network of hexagons and pentagons, forming a hollow sphere with remarkable stability and unique chemical properties. Discovered in 1985 and named for the architect Buckminster Fuller, whose geodesic domes share a similar structure, fullerenes have found applications in diverse fields, from drug delivery to electronics, thanks to their unique combination of strength, conductivity, and versatility. Returning to the molecular level, let's examine the humble methane molecule, CH4, a simple yet essential component of natural gas. Its structure is a perfect example of the tetrahedron in action. A single carbon atom sits at the center, surrounded by 4 hydrogen atoms, each positioned at the vertex of a tetrahedron. This tetrahedral arrangement isn't arbitrary. It arises from the geometry of electron orbitals, dictating the most stable and energetically favorable configuration. This specific structure influences methane's properties, such as its low boiling point and its ability to participate in various chemical reactions. While perfect Platonic solids are relatively rare in the macroscopic world, their influence can be seen in numerous natural forms that approximate these shapes. Consider the pomegranate, whose segmented structure echoes the form of a dodecahedron. Or certain mineral formations, like pyrite crystals, which can exhibit near-cubic forms. Even the intricate hexagonal cells of a beehive, while not forming a closed Platonic solid, reflect the efficiency and stability of hexagonal packing, a close relative of the Platonic solids. These natural forms, while not perfectly regular, suggest nature's tendency to favor the underlying principles of stability, efficiency, and elegance embodied by the Platonic solids. Finally, we venture into the fascinating realm of quasi-crystals, materials that challenge our traditional understanding of crystal structures. Unlike regular crystals, which have repeating patterns in all directions, quasi-crystals exhibit long-range order but lack translational symmetry. Their atomic arrangements are non-periodic, creating fascinating patterns that never quite repeat. Remarkably, the dodecahedron, a shape absent from regular crystal structures, emerges in the world of quasi-crystals. Aluminum-manganese alloys, for example, can form quasi-crystals with dodecahedral symmetry, exhibiting unique properties like low friction and high hardness. These unusual materials, with their intricate and non-repeating patterns, offer a glimpse into a world beyond the familiar, where the dodecahedron, once relegated to the realm of abstract geometry, finds a tangible expression in the material world. Our exploration of nature's blueprint has revealed the pervasive influence of the Platonic solids, from the microscopic to the macroscopic, from the ancient to the cutting edge. These five perfect forms, once whispered about by Greek philosophers, now stand as testament to the deep connection between mathematics and the natural world. They are nature's preferred building blocks, shapes that embody stability, efficiency, and an elegance that continues to inspire awe and wonder. As we continue our journey, we'll discover how these shapes, so simple yet so profound, resonate not just in the natural world but also in the realm of human creativity, from art and architecture to music and even the very structure of our universe. Chapter 6. Harmony of Duality. We've journeyed through the geometric landscape of the Platonic solids, marveling at their perfect symmetry and their unexpected finiteness. But our exploration wouldn't be complete without delving into one of their most captivating secrets: the elegant principle of duality. Duality, in the realm of Platonic solids, is a dance of reciprocity, a graceful exchange between vertices and faces that reveals a deeper harmony within this special group of polyhedra. Imagine holding a cube, its 6 square faces familiar and comforting. Now, picture connecting the centers of each adjacent face with invisible lines. As these lines converge, a new shape emerges within the cube's embrace: an octahedron, a delicate structure of 8 equilateral triangles. This octahedron isn't just contained within the cube, it's intricately linked to it, its vertices touching the centers of the cube's faces, its faces cradling the cube's vertices. The cube, with its 8 vertices, 12 edges, and 6 faces, has given rise to its dual, the octahedron, with its 6 vertices, 12 edges, and 8 faces. Notice the beautiful reciprocity. The number of vertices and faces have swapped places, while the number of edges remains the same. Now, reverse the process. Start with the octahedron and connect the centers of its triangular faces. As the lines converge, they trace the outline of a cube, nestled perfectly within the octahedron's embrace. The octahedron, with its 6 vertices, has birthed a cube with 6 faces. The 8 faces of the octahedron have given rise to 8 vertices in the cube. The 12 edges, the threads connecting vertices and faces, remain constant, a shared bond between these dual shapes. This reciprocal relationship, this duality, extends to another pair of Platonic solids: the icosahedron and the dodecahedron. The icosahedron, a shimmering jewel of 20 triangular faces and 12 vertices, gives rise to its dual, the dodecahedron, a complex structure of 12 pentagonal faces and 20 vertices. Connect the centers of the icosahedron's faces, and you'll trace the edges of a dodecahedron. Connect the centers of the dodecahedron's faces, and you'll find an icosahedron nestled within. Again, the number of vertices and faces interchange, while the 30 edges remain constant, a shared testament to their interconnectedness. The tetrahedron, however, stands alone in this dance of duality. It's a solitary figure, perfectly balanced within itself. Connect the centers of its 4 triangular faces, and what emerges? Another tetrahedron, identical in form, a perfect reflection of itself. The tetrahedron is self-dual, its 4 vertices and 4 faces interchanging seamlessly, its 6 edges remaining constant, a symbol of self-sufficiency and inherent balance. It's a unique phenomenon within the Platonic family, a shape that embodies both the giver and the receiver in the duality exchange. This concept of duality is beautifully captured by the Schlafly symbol, a concise notation used to describe polyhedra. The Schlafly symbol for a Platonic solid is represented as p, q, where p denotes the number of sides of each face and q represents the number of faces meeting at each vertex. The cube, with its square faces, 4 sides, and 3 faces meeting at each vertex, is represented by 4, 3. Its dual, the octahedron, with triangular faces, 3 sides, and 4 faces meeting at each vertex, is represented by 3, 4. Notice the simple yet profound elegance. The values of p and q are simply interchange, reflecting the swapping of faces and vertices in the dual relationship. The icosahedron, with its Schlafly symbol, 3, 5, and the dodecahedron, with 5, 3, demonstrate the same elegant interchange. The self-dual tetrahedron, with its Schlafly symbol, 3, 3, stands as a testament to its self-contained symmetry, the values of p and q mirroring each other perfectly. Duality isn't just a mathematical curiosity. It speaks to deeper themes of completeness, harmony, and balance within this special group of polyhedra. It suggests that these 5 shapes, though distinct, are part of a unified whole, interconnected by an underlying order. The dual pairings reflect a balance, a symmetry that reinforces their special status as the only 5 regular convex polyhedra. Visualizing duality can be a powerful experience. Imagine the dual polyhedron nested within the original solid, their vertices and faces touching, their edges intertwined. This nesting isn't a static arrangement, it can be repeated infinitely. Imagine a cube within an octahedron, within another cube, within another octahedron, and so on, shrinking infinitely inward or expanding infinitely outward, a visual representation of the infinite nature of these geometric relationships. This visualization reinforces the interconnectedness of these shapes, their dual nature bound together in an endless embrace. It's a glimpse into the infinite, a reminder that even within the finite realm of the 5 Platonic solids, there lies a boundless depth of geometric relationships waiting to be explored. Duality, then, is more than just a geometric principle. It's a philosophical concept, a reflection of the interconnectedness and balance we find in the natural world and, perhaps, in the universe itself. It's a concept that has resonated throughout history, from the ancient Greeks who saw these shapes as representations of the fundamental elements to modern scientists who find them echoed in the structure of molecules, viruses, and even quasi-crystals. The Platonic solids, with their perfect symmetry and their elegant dual relationships, continue to inspire awe and wonder, inviting us to delve deeper into the hidden harmonies of the geometric world. They are a testament to the power of mathematics to reveal the underlying order of the universe, a reminder that even the simplest shapes can hold profound secrets, waiting to be unlocked by those who dare to explore. The 5 Platonic solids, uniquely defined by regular polygon faces and identical vertex arrangements, are not merely beautiful abstractions but reflect fundamental mathematical principles, notably Euler's formula and the concept of duality. Their limited number arises from geometric and topological constraints, yet their influence extends far beyond abstract mathematics, echoing in natural structures from crystals and viruses to fullerenes and quasi-crystals. This deep connection between mathematical principles and the natural world suggests a fundamental order underlying the universe, inviting further exploration into the interplay of geometry, topology, and the physical world. What other natural phenomena might these shapes illuminate? Share your thoughts and questions below. Like and subscribe for more explorations into the wonders of mathematics. Never stop questioning. The universe is full of fascinating secrets waiting to be discovered.